All right, so let's now use our knowledge to create some kind of example. And I came up with a cable generator for a spooky sci-fi scene. I don't know. You could create cables with that between buildings or whatever you want, but I found this is maybe something that hasn't been used too much. So what we have here is some kind of, I don't know, some android that has some cables connected to some brain sphere. I have no idea. So what we want to do is we want to create some random cables between the objects, and we want to use the vex code that we learned so far: min, pos, distance, add point, add prim, all this kind of stuff. So for this, we will connect just the upper part of our android here, which of course, as you can see, is Tommy, the way he looks on the weekends, and then we have this weird sphere that we want to connect to. Now you don't necessarily have to, but what helps here to make it a bit easier is to just scatter some point on the sphere so that we define where the cables should come from. You could even limit this just to the front part and so on. You get the idea. We can still do this later. Let's start with the setup. So what we want to do is we want to find for those points the closest position on the surface of our android. So we want to work with these points, and then the second input is our android, and I call this cable gen. So let's go. So first of all, let's for each point find the min position, which of course is a vector. And actually let's work with attributes this time so that we can better debug this. And we look for the min pos on the second input, our android, based on our current position. And then we should already get some. Great. So these points found the closest position on our android here. Of course, you could have used near point as well, but then you would have to define your contact points here, which is also fine. So it's up to you how you want to adjust this concept. And now let's, to move forward, because I would always recommend to do what you know, not what you don't know first. So what we know is that we will need a second point if we want to create a curve between those two positions. So let's create a new point. Of course, we can use add point for this. And we want to create the points on the current geometry. And let's see again what the logic here is. You need the geometry and the position of the new point. And we already have that. It lives in P2. The advantage of this is here you can already see where the points will end up being. And as you can see, this is currently what we're doing. We just create those points on the closest position to our sphere points. What do we do with that now? Well, we could create actually a line between the two. So let's create an add prim, and then the logic here is we need a geo handle, of course, a type of geometry, and then we can give it the points we want to connect with a line in our case. So the type of geometry we want to create is a curve, so it's polyline. And the 2 points we want to connect is the current point, which has the point number ptnum. And the second point is, the new point we just created, and we obviously forgot something. We forgot to be able to reference the point number of this new point. So let's make sure that we save that, for example, in an internal variable. You could make it attribute as well, doesn't matter. So let's call this np for new point, which is an integer, and use that as a new point that we want to connect with. And there you go. Basically, that's the main part. We now have an automatic generator of points. And the cool thing now is actually when we move the sphere around, this connection will change depending on, of course, what the closest point is. And we can also change the amount of points that we want to work with. So if you want more cables, no problem. And if you want fewer, also no problem. What we could do now actually to make it a bit more interesting, to make sure that the points are not scattered all over the sphere, but only at the front. The easiest way to do this is just to clip them. There are more complicated ways of calculating this automatically, but why make our lives unnecessarily hard? And then we just take this part and that should be fine. And now we clipped this part of our sphere. And then if we scatter on that, all points kind of look at our android. So if we merge this result now, so here we have our sphere and our android, and we add those curves now. It's not too bad, but it's still a bit boring. And what I notice is I actually always have a connection, no matter how far away I am. So what would be a bit cooler instead is to make sure that it only has a connection in a certain distance. There are multiple ways of doing this. The first one is to use a built-in function that the min-pos already has. When we look at the help again by pressing F1, you can see there's actually already a built-in max dist. And this is quite cool, so that we can, for example, say only find the closest position in a distance of 2 meters. And this will result in a more dynamic connection, so it will disconnect if the distance is too high. But if we wouldn't know that, or we wouldn't care or whatever, then we could do something else, and that is we could just calculate the distance ourselves. So we could create the distance between the current position and the min pos we found, of course, with a distance function. And all we need to do is we add our position and the second position we found from min pos, and now we have the distance in D. And what we can now do is we can add an if statement, and only if that distance is smaller than a certain distance that we want to put on a parameter, then should the curve be created, including the point that is part of it. And now we have our own parameter called dist, and we can move this up and change the distance that is used here for our code. Again, there's a built-in version in the min pos that would do this automatically, but I find it interesting to edit ourselves manually. So now we have that, and this is basically everything we've learned so far in one example. And let's make this now a little bit more interesting. What I would actually do here is I would simply curve them down with a couple of nodes in Houdini. Because what you can do is you can use a resample first to give our curves a couple of points that we can actually move around. But the funny thing is now we will actually lower this not to a certain distance, but we will only give the whole thing exactly 3 points so that we can find the center of our curve. And what we want to do now is we want to move down this center point and then create a curvature from that by just interpolating the curve. That's the easiest and quickest way I know, and I just wanted to share that with you. So what can I do though to find the center point? There is no way really based on the point number or something to figure out which one is the center one, but we can use actually the curve u function that we already seen. And when we check what curve u number the center point has, surprise, it's exactly 0.5 because it's exactly in the center. So we can simply use a transform node and create our own rule here saying that the curve u attribute has to be 0.5, and then we move the point and make sure that you have the group type set to points down actually, there you go, a little bit, there you go, and then it looks much more curved basically, but of course it looks horrible. The trick now is to simply use another resample and turn this to subdivision curves, and then you can see we have a nice curved version of that, and we can even lower the whole points further, and then it looks a bit more like cables that are hanging around. And of course with a poly wire or maybe a sweep, we can now make this look a bit more interesting by using a round tube. And we have a lot of problems when we're trying that. The reason is that there is a normal attribute. So let's make sure we get rid of this because it always creates problem with a sweep. So goodbye normal, there you go. And now it works much better. And we define the radius. And now we have our, actually let's also increase the number of subdivisions to make it nicer. And now we have a much nicer version of our curves, there you go, that are connecting our Android with our spooky, I don't know, brain sphere, whatever. So what we can still do, like we saw, we can still move the sphere around, which is kind of cool because then we can, find something that we like. We can of course also change the amount of cables that we want, maybe a huge amount of them, also interesting. And this by itself is already pretty cool. But let's add an additional level of complexity to this. And that is when you look at the, hanging down of my curves here, every curve hangs down the same way. I want a bit more variation. And one easy way of doing this is, and let's quickly reconnect this a little bit. Instead of using a transform to move the center point, we could, for example, use another point wrangle to move those points by a random amount. So to move something down by a random amount, we know we can just take the y element of the position and subtract from that a random number based on the current point number. Of course, what will happen now is that each point moves down. So we want to limit this again to only the points that have a curve u of 0.5. Again, just to be safe, make sure that you change the group type to points, but you can see it already works. And now, of course, it's sometimes a bit too strong. So we just multiply our randomizer with maybe 0.5. And we can even, change the seed by adding an offset to the random input. And then you can even, okay, it has to be an integer though, but you can still maybe doing this like this. So let's delete this, right click, more, delete spare parameter. We could have also used this, could have done this up here in the parameter interface. And now I changed this to an integer instead. And I think this is much nicer because now I can change the seed if I don't like what I see. And now the result is a bit more varied, because each curve has a slightly different length. So yeah, so this is an easy way of doing something like that. We will see in a later video that you can also do different ways of finding the connection point, not only the min pods, because that result in multiple points finding the same position. We will see how to find multiple positions and then based on randomness choose them, but that's a bit too early for that. For now, I just wanted to show you what you can do with the knowledge we have so far. Let's add a little bit to this to make it a bit more interesting, and that is let's add some connect points here, just as a small little interesting note, because here we have actually a couple of points, and if you create a normal for the geometry that you use, and the same is here for our Android, I created a normal attribute for each of them. Actually, I didn't. I only created on the vertices, but I wanted them on the points. And let's do the same here for our Android. There you go. And now each point has a normal. And what you can see is when we look at the cable gen, the points that we just created, some of them have normals. And of course, it's the ones that were already there that we created the curves from. But the normals from our Android are not taken into account with the second points that we created, because it doesn't know about the normals there. There are multiple ways of solving this. One way would be to just use an attribute transfer and simply steal the normals for the points from our Android. Just make sure that you only copy the normals. And here you can see they worked. So let's make sure that we lower the distance threshold so it doesn't overwrite our sphere normals. And now that, as you can see, is a really quick way of solving this. So I do this quite often. If you lose some information, you just steal it back from somewhere else with an attribute transfer. But if you really wanted to do that with Vex, then I want to show you this as well. What we can do is we just steal from the closest position of our Android. It's not identical with the min pos, but it's good enough for our case. So let's do this. So the nearest point is near point, of course, 1 VP. And then from that, from this position that we found on the Android, we steal the normal. So let's call this vector Android normal. From this point, from the second input, we steal the normal from the near point that we just found. And now the question is, how do we apply this vector to the new points that we just created down here? And you can do that with a set point attribute, or attrib for short. And the way this works is, let's quickly look into the help. It's pretty straightforward. It needs a geo handle, of course, then the name of the attribute, the point number that we want to write to, and the value. Pretty easy. So in our case, let's keep that. It is for the current geometry, for the newly created points, we want to add the normal attribute for which point number, NP, which is where our new point number lives. And then we want to save the Android normal on those points. And there you have it. Now we have the normals, as you can see, on our newly created points as well. So what do I do with all this? I just copy some kind of tube or something. There it is. That will be our connection. And let's make it much smaller, of course. And we copy this with a copy to points to our cable points. There you have it. The only problem is they are oriented in the wrong way, and we know why, because the tube will orient to the normal. That means we have to rotate it so it looks at Z. And this is once again by just rotating it by 90 degrees in X. And there you go. Now we have a contact point. Just let's make it a bit smaller, maybe with a transform. There you go. And now we have a contact geometry, which always looks a bit nicer to have when you have cables. There you go. And I just realized I used the wrong points. Why is that? Oh, yeah, interesting. We still have the points left over from the sphere when there are no curves. So that's interesting. I mean, it doesn't look bad, right? It's actually, I kind of like it the way it is right now. But, and actually, let's quickly solve the normal. There you go, and that looks nicer. But if you don't want that, if you want it to be only where the cable is, that should be straightforward for you, because we already have this if check. Only there will be cables created when there is a certain distance threshold reached. If this doesn't happen, we just add an else. If it is not in the right distance, then we just remove the current point. And then our connection points that are don't have cables will be gone. So yeah, so I'm thinking what else I can show you. One more thing I think I want to add to this, because I think it's kind of interesting. Let's go back to this moment where we had multiple points. Actually, yeah, where we just moved down the single point. Like I explained, quickly use the ramped version because that's also an interesting one. So we use a resample node again to resample our curve with multiple points. And instead of only creating one in the center and moving that one down, we use a point wrangle and make sure that your resample is actually creating a curve U attribute so that we know for each point where it is along our curve. And the cool thing about the curve U attribute, unsurprisingly, it's between 0 and 1. And we can use this to our advantage, because this way we can say for each point the Y element, subtract that please by a ramp. And this ramp, let's just call it ramp, doesn't matter, needs to be fed by something between 0 and 1, and this is exactly what we're using here. We're using the curve U for each point to read from this curve right here that we just created how far it should go down. This results in the first points to not go down and the further points further down the line to go down quite a lot. But what we actually want is the ends. We don't want to move, we only want the center point to move again. So now this is a weird, annoying angle again, but the cool thing is we can now use a different interpolation like Catmull Rom, for example, for each point. And then you can see it is actually more round, and you could, and this is a cool thing about it, now use this ramp here to change the profile of your hanging curves. And as you can see, they are once again all hanging down by the same amount. So if you want it, you just multiply the whole thing again with a randomizer. And okay, this is tricky now. You don't want to randomize it by the current point number, because then each point gets a different hang down. We want to do this based on the curve. A way to do this is by calculating for each curve an attribute, and we know how to do this with a connectivity node. And then each point has a different class attribute telling you on which curve it is, and we use this in our randomizer to define how much it should hang down, because each curve should use that, not each point. Oops, class. And this way it will be different for each curve but not for each point. And then you have maybe an even nicer version of that instead of just taking the middle point and resampling that. But you know, both, in my opinion, make sense, and one is a bit easier and the other one may be a bit more flexible. And when I use the sweep without an attribute delete, I get the problem again of having the normals that destroy everything. So let's delete them here as well. And let's now use this version instead of our first version. So yeah, and now we have maybe an even nicer version of our cables. You know, you decide. Okay, I will stop here. I just wanted to, you know, play around a little bit, experiment with what we know so far. And this is now our curve generator to create some spooky sci-fi scene. And the cool thing is, of course, we can still move around our sphere here to change the position and the way the curves will look like. And also we can change the amount of points so that we have a denser cable setup. And this would be my argument when you would need a setup like that, because nobody wants to model this by hand. So yeah, just playing around a little bit with the stuff we know so far. So I hope this is helpful. Thanks very much and see you later. Cheers.